Swayam Prabha. Digital India. Educated India.
And we get something. The main point is that this now includes the left hand side of each equation is the total current flowing out of the nodes, that is current flowing out of each node in every branch connected to that node. Okay, so when I add up these two, what it means is it's the sum of all the currents flowing out of N2 and N3 together. Okay, so let me do that. I will get minus G12 plus G13 times V1 plus G12 plus G22 times V2 plus G13 plus G33 times V3 to be equal to I3. So the important point is when I add this plus Ix here, okay, so the minus Ix here cancels with plus Ix there. Okay, because I have connected, I have taken the two nodes between which the voltage source is connected. One of them will have plus Ix, the other one will have minus Ix, so they will cancel. Okay. So that is the important part. So what does it mean now? This the left hand side here is the total current flowing out of N2 and N3. Okay, and any current that is flowing between N2 and N3 will get cancelled out because it will have plus in one contribution and minus in the other contribution. So essentially what we are doing is forming what is known as a super node, that is a combination of multiple nodes. In this case V2 and V3. We always combine the two nodes across which the voltage source is connected and write KCL in terms of all the currents flowing out of that node. Okay, for instance, we add that current that is flowing out of the super node, this current that's flowing out of the super node, the current here and the current there and the current there. Okay, so we write it as the total current flowing out of the super node to be equal to the total amount of independent current source currents being pumped into that node. Okay, now you can see that the current in the voltage source is not flowing out of this super node or into the super node. Okay, so it is not cutting the super node, so it disappears from the picture. Now this is a technique to reduce the number of equations and not have this auxiliary variable. Okay, so typically when you do hand analysis you would use this, and by introducing a super node you will end up with cancelling Ix and have only one equation. And we have this extra equation, that is we have still lost one equation. Originally we had 3 for the 3 nodes. Because of the voltage source and combining these two nodes, we have a single super node equation. So we have 2, this is 1 and that is the other one. Okay, but we do have the additional constraint imposed by the voltage source. So finally we have 3 equations in 3 variables. Okay, and this is one fewer than what we did using modified nodal analysis. So for hand analysis, when you have voltage sources, you introduce super nodes and go ahead with the analysis. Okay, now one very important thing is that when I say I combine these two into a super node, I am not shorting this to that. I still retain this voltage as V2 and this one as V3. Okay, so all the currents must be expressed appropriately. That is, the current in R12 will be V2 minus V1 times G12. R22 will be V2 times G22, whereas R33 would be V3 times G33 and R13 would be V3 minus V1 times G13. Okay, so the voltages should not be changed. It's not like we are shorting them. It's just that we are writing the KCL for the combination of the nodes. Okay, any questions about this? Okay, there was a question about how do we choose the direction of Ix. Now, in principle, it doesn't matter because it will always contribute plus Ix to one side and minus Ix to the other side. But as always, use passive sign convention. So if the voltage source has positive on this side and negative on the other side, that is the voltage source symbol is drawn with the voltage is defined with positive on the right side and negative on the left side. You choose Ix also to be flowing from right to left. Okay. Okay. And finally, you have the voltage source equation. Okay. So then you can again invert the matrix and get the result. Okay. Now when I say invert the matrix, that's how you would set it up and solve on a computer. When you're doing hand analysis, obviously you will eliminate variables or eliminate variables one by one, sort of by trial and error and so on. But whatever it is, if you solve this, effectively you have inverted the matrix. Okay. So that's what I mean. Now next we take other components which we have so far not included, that is some types of controlled sources. Okay. So let me again have the same exact same circuit as before. I will use this without the independent voltage source. We can also include that one if necessary. Okay. So this is the resistor R13, right? So let me take this. I have my original circuit and also the matrix that is set up. Okay. So this is the original stuff that I had. Now to this, what I will do is I will add a voltage controlled current source. And let me say I add it here Okay, and this current source equals some gy times V1 minus V2. Okay, so this is my new circuit. Now what I would like to know is, first of all, which equations get modified. Okay, which rows get modified. Okay, I will set up the question. Yes, Raj, please go ahead. The question is, which of the node equations get modified? Okay, only for node 1, only for node 2, only for node 3, or node 1 and 2, or node 2 and 3, or something else. Okay, it's clear that this current source is added to node 3. Okay, now if it was between two nodes, then two node equations would get modified. In this case, this extra current source that I added is added only to node 3, so only N3 will get modified. Okay, now the next question is, how will it get modified? Okay, where will this gy appear? Is it in column 1, column 2, or column 3? Column 1 corresponds to coefficients of V1, column 2 to coefficient of V2, and column 3 to coefficient of V3. Okay. So, which of the columns get modified because of this control source? Is it column A, that is coefficient of V1, column B, coefficient of V2, or column C, coefficient of V3? Or is it something else? Okay. So the question is, because of this voltage controlled current source, which of these columns will get modified? Is it this one, is it this one, or is it that one, A, B or C? Okay, or is it more than one? Okay, many of you answered that it is the third column that will get modified. Okay, but that's not correct. I think one of you said that it is these two, that is coefficients of V1 and V2, that will get modified, and that is correct, because you do add it to the third row because it belongs to the Kirchhoff's law for node N3. But if you look at this, it is Gy times V1 minus V2. Okay, so the value of the current is related to the voltages here, and those are the ones that will get modified. Okay, because if you look at this current, if it was a resistor, the current in this would be related to V3. It would be V3 times G33, whereas this controlled current source, the current is Gy times V1 minus V2. Okay, it's related to voltages somewhere else. So it is this basically coefficients of V1 and V2 that will get modified. Okay, I hope that is clear. If there are any questions, I will take them. Okay, so the point is that VCCS connected to N3, so N3 equation modified, and the voltage controlled current source is controlled by V1 and V2. So these coefficients get modified. Okay, and how will they be modified? So first my question is, what happens to this coefficient? Minus G13. Originally the coefficient of V1 in this equation is minus G13. How will it get modified? What happens to minus G13? So the coefficient of this one will get modified and this one also. So how will this be modified? So one of you answered this. Basically the current drawn out of this is Gy times V1 minus Gy times V2. Okay. So because plus Gy times V1 is flowing out of this node because of the controlled current source, this minus G13 will be modified to minus G13 plus Gy. Okay. Now similarly, the current drawn out has minus Gy times V2. Okay. So that minus Gy gets added to this one, and this will be minus Gy. Okay. So now this is how you can handle voltage controlled current sources. You don't need any extra variables or equations. because this voltage control current source simply adds currents to one of the nodes or maybe two nodes. Okay, in this case the voltage control current source is connected between node N3 and the reference node, but it could be connected, let's say, between node 2 and node 3 also. So wherever it is connected, it will modify those equations, and which of the coefficients will get modified, that depends on the controlling voltage. In this case the controlling voltage is V1 minus V2, so the coefficients of V1 and V2 will get modified, and the signs you choose appropriately. Anything on the left hand side is a sum of currents flowing away from the node. So Gy times V1 is flowing away from the node, so plus Gy gets added to the coefficient of V1. Minus Gy times V2 is flowing away from the node, so minus Gy gets added to the coefficient of V2. Okay, is this clear? Are there any questions? So one thing you observe is that because of the voltage controlled current source, this matrix is not symmetric. Okay, so if you had only independent voltage sources and resistors, it would be symmetric, but if you have voltage controlled current sources, it's not going to be symmetrical. Okay, so now we know how to handle these extra cases. First we started with only resistors and independent current sources, then we added independent voltage sources that you can handle either by an auxiliary variable, which is easier when you are setting it up for the computer because it's more systematic, or you can identify the voltages to which, the nodes to which the voltage source is connected as a super node and write a single equation, and that is more useful for hand calculation. And if you have a voltage controlled current source, then you have to modify the matrix, it will become asymmetrical, but in general, so that also you can do. It will modify the equations at nodes to which the control source is connected, and some coefficients will get modified. Okay, so next we will take another example with a different kind of control source, which is a voltage controlled voltage source. Okay, so let me take this circuit again, and what I will do is, instead of R33, I will have a voltage controlled voltage source. Okay, and this voltage, I say, is some K times V1 minus V2. Okay, so this control source is K times V1 minus V2. So what do we do here? First of all, just like a voltage source, when we had an independent voltage source, add an extra variable. Okay, and that is the current through the voltage source. I will still call it Ix. Okay, so the equations will be exactly the same as before, with this Ix substituting for the current that was flowing in the resistor. Okay, so if I write down the equations quickly for this one, what happens is, at node 1 nothing is changed, so we have G11 plus G12 plus G13 minus G12 and minus G13. Okay, and at node 2 also nothing is changed, so we have minus G12 plus G22 plus G23 minus G23. So this is resistance R23, by the way, not R13. And then at N3 we have to change it. So the equation here would be, at N3 would be minus G13 times V1 minus G23 times V2, and here we will have the sum of conductances, which is G13 and G23. But also the current flowing out includes Ix. Okay, so my variable vector includes Ix. Okay, and it's flowing away, so I have a plus 1 over here, and Ix doesn't appear in the node KCL equations for node 1 and 2, so I have 0 over there. And finally, I have to write the equation for the dependent source. Okay, now in case of the independent source, we wrote for instance V3 minus V2 equals V0, and the independent source value was on the right hand side. In case of the dependent source, V3 equals K times V1 minus V2, but V1 and minus V2 themselves are variables. So what we do is, V3 in this case happens to be K times V1 minus V2, but V3 itself is V1 and V2 themselves are variables. So we take it over to the left hand side. All the variables will be on the left hand side. So V3 minus KV1 plus KV2 equals 0. Okay. So what do we have? Minus K plus K and V3, that is plus 1 and 0. And I don't have the room to write the source vector, so that I will copy over to the next page and write. Okay, and this equals the total independent current source current flowing into node 1, which is I1, into node 2, which is 0, into node 3, which is I3, and the last one, this is simply the equation for the the dependent voltage source, so this is just 0. Okay, so again we have an extra variable Ix and an extra equation for Vc Vs. Okay, so the way to handle the dependent voltage source, that is voltage controlled voltage source, is exactly the same as handling the independent voltage source. You define an auxiliary variable and go with it. The only thing is that when you write the equation for the voltage controlled voltage source, you group all of the variables to the left hand side. Okay, so that's all that is there to it. Any question? I think one of you had this question, what do you do when you have a voltage controlled voltage source, and this is what you do. Now the alternative method was to use a super node. I am going to go to that, but before that, if there are any questions about this, I will take them. Okay, it appears there are no questions about this, but there are some questions about what we did before with the voltage controlled current source here, and I think the question is why this entry is minus G13 plus Gy. Okay, so that comes from writing the KCL for this node. Let me write it in a different color here. So the KCL for this node includes the current there, plus the current there, plus the current there, plus the current there, equals the current flowing in from the independent current source. So the current in R13 is G13 times V3 minus V1. Current in R23 is G23 times V3 minus V2. And the current in R33 is G33 times V3. And the current in the dependent source is plus Gy times V1 minus V2. Okay. So if you look at the coefficient of V1, it is plus Gy minus G13. Okay. So V1